Welcome back, students. So we are continuing the discussion on wind energy. So today we are going to discuss about types of wind turbines and its components working. So there are two types of wind turbines: horizontal axis wind turbines and vertical axis wind turbines. As the name suggests, horizontal axis wind turbines are having axis of rotation parallel to the ground or perpendicular to the structure or the support. So this is the horizontal axis wind turbines are most commonly used nowadays for its strength and a better efficiency when compared to the vertical axis turbines. But the disadvantage is one may require very heavy equipment for lifting the nacelle, blades, gearbox, etc. to a very higher level, as well as requires very heavy support to support these things. I'll show you the photographs. In addition to that, additional yaw control mechanism also will be required for this horizontal axis type of wind turbines. Whereas in vertical axis wind turbines, the axis of rotation is perpendicular to the ground where it is mounted. Okay, so whenever there is wind available in the downward direction, so vertical axis wind turbines are most preferred. Also, it is less affected by frequent wind direction changes. In the case of horizontal axis wind turbines, this wind direction changes has to be taken care by this yaw control. In the case of VAWT, that is vertical axis wind turbines, the maintenance is very easy because the shaft and the various components like generator, gearbox, the entire nacelle is mounted near the ground level, so you no need to climb up a very large tower, tall tower to maintain the components. But the efficiency when compared to HAWT is poor for vertical axis turbines because of air track at the ground level. So these are the two types of wind turbines. You can see this is horizontal axis, the axis of rotation. The axis is perpendicular to the plane of projection here, which is parallel to the ground, and here this is axis is perpendicular to the ground. The rotation will be taking place with respect to this horizontal, the vertical mounting. Okay, so mostly the turbines will be having 2 to 3 blades to have a better efficiency. So it is experimentally found that 3-axis wind turbine will be having a better efficiency when compared to other axes. So that's why this optimized configuration is being used nowadays. In addition to the experimentation, there are finite element techniques to determine the better blade design, better efficiency, and so many terminologies are optimized before actually making the wind turbine blades and wind turbine. So there are two categories of vertical axis wind turbines. The names are Darius and wind turbines and Savonius wind turbines. So Darius wind turbines are lift force driven and Savonius are drag force driven. There is a difference between them. So let us examine the various components of a wind turbine. So here a side-by-side comparison of a horizontal axis and vertical axis wind turbine is given. You can see there should be a support structure, okay, and a tower on which the entire components are mounted, and you can see the different blades and shaft of rotation here. Okay, this is the rotor diameter, the dimension, this is a blade, and there is a gearbox, the purpose of which will be discussed later. and there is a generator to convert mechanical energy to electrical energy. So first, the kinetic energy of the wind will be converted to mechanical energy using this blades, fine, and the gearbox is required to synchronize the speed of rotation of the shaft with the electrical generator. Okay. Now the entire structure in which the gearbox and electric generator are mounted is called as a nacelle. A nacelle is the name for the entire box kind of arrangement wherein gearbox and generator are arranged and mounted, and various controls, and the generated electricity will be drawn downwards through the tower and it can be fed to the grid, right? So whereas you can see here in a vertical axis turbine, the entire nacelle is placed at the ground level. Yeah, there are different configurations, Savonius, Darius configurations, and the design of blades. See here, various parameters of the wind turbine and wind turbine blades. This is typically related to the vertical axis wind turbine. So, in short, you can note down the various components. There should be a rotor on which the blades are mounted, and 2 or 3 blades, then a low speed shaft and a gearbox. A gearbox is placed between low speed shaft and high speed shaft, and the generator is mounted on the high speed shaft. Rotor is mounted on the low speed shaft. Okay. So this is in the order, starting from the left side. If you see the previous diagram, okay, this is in the order. Then electric generator, then there should be brakes. There should be brakes and controller to control the speed of the turbine, and the controller should be there to maintain the proper speed and to deliver the generated electricity to the grid. Yeah, you can see a more um, clear picture here on a horizontal axis wind turbine, the two different views, side and front views. Yeah, an important term here, the swept rotor area and blade area. This area of the blade, that is the surface area of the blade, and the swept rotor area is this circle represents the swept rotor area. Now, what is the requirement of gear transmission? So gear connects the low speed shaft to the high speed shaft. So low speed shaft is connected to the rotor wherein the blades are mounted, and the high speed shaft is the one on which the generator is mounted. So typical rotor will be having a speed of 30 rpm to 50 rpm. Okay, but as the generator speed may be around 1000 to 1500 rpm. So we need to increase the speed from 50 to 1000 or 1500. So obviously we require a generator here to manipulate the speed according to the requirements of the generator, because then only the current electricity will be generated. When you rotate a shaft with the 30 to 50, the required electricity may not be generated. So we need to synchronize the speed or manipulate the speed using the gear transmission lines or gearboxes. Now, in the design of a gear system, additional requirements, additional considerations are heat dissipation, power losses, sufficient cooling should be provided, excess heat generated should be dissipated, then design should be compact since it is mounted on a very high level in the case of HWT, weight, and the bearing, because frequent maintenance may not be possible, right? It is very difficult if it is stalled. So the bearing, lubrication, the heat dissipation, all these things should be considered properly before designing a gearbox, gear transmission system for a wind turbine. Now turbines start generating power at lower set wind speed at, for example, 5 meters per second. Okay, so power increases with increase in speed up to a rated wind speed and rated power. Now, after attaining the rated power of 250, for example, kilowatts, say for 15 meter per second wind speed, the power output remains constant at rated power between the rated wind speed and the cutoff speed. So turbine stops operating speeds higher than the rated speed due to safety reasons. So if the speed becomes excessive, if the wind speed becomes excessive, still the generator will be generating only the rated power, because we need to limit the speed so that after the maximum power is generated, the power regulation mechanism will maintain that power alone without increasing beyond that. This is for safety reasons. So power control, for example, when the wind speed changes in the previous diagram 15 to 20 meters per second or the rated power range, the rotor speed also changes from 30 to 50 rpm. So need to address the rapid acceleration in this power control system. So turbine power is regulated, that is after attaining the peak power, there is no hike in the power generation. So these are the different power control methods: pitch control and stall controls. So in the pitch control, blade pitch and blade angle of attack is decreased with wind speed greater than the speed. So that much wind alone will be coming onto the blade, and the rotation will be, wind speed will be regulated. I mean, the rotor speed will be regulated. So that will require a sophisticated control mechanism. On the other hand, stall control, blades are designed in such a way that with increase in wind speed, the angle of attack increases. So these are the terminology associated with dynamics of rotation of components, angle of attack and all. The pressure variation at the top and bottom surface of the blades changes, causing the flow separation and water shedding. So the stall control kills or stops the lift forces and leads to blades stalling. So blades will slowly come to a stop without increasing the speed further. Again, it will require very sophisticated blade aerodynamic design. The aerodynamic design of the blade should be very much sophisticated in order to maintain the speed of the blades under this stall control. Again, there is another control known as yaw control. The rotor is partially pushed away from the wind direction at higher levels. So it will be slightly moved whenever the speeds of the wind is increased beyond the set limit. The rotor will be partly pushed away. You might have seen in the windmills several times. The wind rotor will be positioned in different directions, different angles. So there are three categories of electricity generating windmills: small, medium and large, depending on the power it can generate. So for small windmills are suited for homes, farms and remote applications like water pumping, telecom sites and ice making, whereas the intermediate or medium type windmills, which can generate 10 to 250 kilowatts of electricity, are suitable for powering a village hybrid systems, whereas another mode of electricity is also available from the wind or solar, like that, then for distributed power. Large windmills are mainly suited for central station wind farms for distributed power to the grid, whereas the entire district or state is required to be powered. Okay. So here in this slide, I have given the three categories of the windmills as well as approximate electricity generation from windmills as well as the applications. So please note down the different things are being discussed in noise levels of wind turbines. You can see here it is very less. It is almost close to a noise level in a home. There is not much noise is generated from a wind turbine, only of the order of 50 to 60 decibels. So, having discussed many advantages and applications of windmills, let us look into the limitations of wind power. The power density is very low. Obviously, we have seen the maximum wind speed is limited, so we need a gearbox. Even though the gearbox is integrated, we need to have a very um, uniform wind speed to generate a continuous power. So power density is very low. So we need to have very large number of windmills to produce modest amounts of power if you want to generate electricity for a community. Then the cost of construction and installation is very high. So initial investment is very high. Then environmental cost, the maintenance and material cost. Then the bird community may get affected in large, especially since they are flying at these levels. So whenever wind turbines are working, the birds may hit on these blades and it may fall dead. So um, it happens. It happens at times. There are several occasions where large herds of birds are hitting the rotating blades and falling dead. And wind power cannot meet large scale and transportation energy needs. That is largely in transportation. Obviously, it is not possible to implement wind turbine. Rather, a solar energy will be more suitable. The future of wind energy can be bright if government provides various subsidies and encourages its use. So technology improvements are likely to have a major impact because it is almost done. Now only the blade design criteria and the various types of designs to improvise the efficiency by reducing the drag and increasing the optimizing the tip speed ratio. All these things needs to be considered in the design stage itself. Wind power can become cost competitive for electricity generation if fossil fuel energy costs are increasing day by day. Okay, so let us stop the discussion on wind turbine. If you have any doubts, you can come back to me in the comments box. So please subscribe to this and on the notifications to get the future videos. I hope the lecture was clear and this is very simple fundamental explanation only. I'm not a person to explain wind turbine components in detail. If you are interested, I may deliver another